Okay, ladies and gentlemen, this is day one of calculating energy changes at phase changes. Okay, if you look at this graph that I have here, time is on the x-axis, y-axis is the temperature. Okay, for this particular substance, and we don't know what substance it is, but I can see right here that I have a flat line, a plateau, and also right here is a plateau. So when I click on the first question is, what is the melting point of this substance? Well, as I'm eyeing this, excuse me, I look and I say my first plateau here is my melting point. So for this particular substance, my melting point is going to be 50 degrees Celsius. Okay, there we have it, 50 degrees Celsius. All right. So then, when I ask the next question, what is the boiling point of the substance? I come back and I find my second plateau here. Here's my flat line. So my second one here is the boiling point, and that's going to correspond to 100 degrees Celsius. So for this particular substance, the melting point would be 50 degrees Celsius. The boiling point's 100. Calculating energy changes at phase changes. HV and HF. That is the heat of vaporization, the heat of fusion. We'll discuss that here shortly. It takes energy to heat stuff up. For a pure substance in a single phase, we can calculate how much energy is needed based on the equation Q equals mc delta T. Well, you might ask yourself, all right, what do all these things mean? Okay, what do these things mean? Well, Q is the energy in joules. Okay, we label joules just simply with a letter J. So if you see anything labeled J, that is energy. M is the mass of the substance in grams. C is the specific heat capacity, and at times you'll hear me just refer to this as the specific heat. And finally, delta T is the change in temperature, and that is the temperature final minus the temperature initial. So the final temperature minus the initial temperature is going to give us the change in temperature. Delta is change, T is temperature. So we just stated it takes energy to heat stuff up. Well, just on the flip side of that is that it it releases energy when something is cooled down. So in order to heat something up, we need energy. In order to cool something down, it is releasing energy. Okay. Here is a chart that is dealing with the specific heat capacity, okay? And we will read with these the specific heat capacity right here. It is the amount of heat required to raise the temperature of 1 gram of a pure substance by 1 degree Celsius. That is the definition of specific heat. And specific heat is a physical constant. It is unique for every pure substance. And can you find the specific heat of water on your reference table? Well, that's going to lead me now back. That's going to lead me to the reference table. So I'm going to exit out of my PowerPoint right now, call up the reference table. Here is the reference table that I have given you. As you can see that I have water on the reference table down here. So here is the reference table for water right at that point. Now, the problem with this specific table is my label right here. I can see that everything in this column is labeled joules per kilogram times degrees Celsius. Well, that's not what I want, because when I'm doing these calculations, I want my label to be joules per gram, not kilogram. Okay? So here is what I want. I want my label joules over gram times degrees Celsius. So what I'm going to do is I'm just going to make a simple conversion, and I'm going to tell you the conversion. Right here, all we're doing is we're going to move the decimal place 3 to the left. So for this specific one for ice, it's going to be 2.1 joules per gram times degrees Celsius. For liquid, it's going to be 4.186. And for the gas, for steam, it's going to be 2.010. So go ahead and write that down on your reference table so that you have those values. And remember, the reason being is that my label up here is joules per kilogram times degrees Celsius, and what I really want is joules per gram times degrees Celsius. So make sure you make a note of that. You can also see the specific heat capacity of many different substances are listed on this particular chart. Let's go back to the PowerPoint. Okay, so now we've checked out the reference table, and we can see that in part 1 of this graph, and you don't know yet what part 1, part 2, part 3, part 4, and part 5, they're just different parts of a temperature, okay, of a boiling and melting point graph. As I can see right here, the temperature is increasing, okay? Is the temperature increasing here? No, that's going to mean something for this. Notice that we don't have an equation up here yet because we don't have a change in temperature. So a change in temperature would mean nothing. That would be 0, and it wouldn't mean anything for the Q here, which is not the case for the second and the fourth. Okay, so we have to have a change in temperature for Q equals mc delta T. So for this particular one, this is where we are at the solid phase. So if this were water, this would be ice. Okay, solid phase of water, ice. Okay, this one right here, Q equals mc of a liquid delta T. We can see that yes, we are again we are increasing the temperature. Let me go back. We are again increasing the temperature, so I will have a delta T. So I can use that. We would use the C of the liquid, which was the 4.186. Here's a straight line, a flat line. Do I have any change in temperature? No. Notice I don't have the mc delta T up there. Here we go now into the gaseous phase. And once again, I am changing temperature. I am getting a greater temperature. So mc of the gas delta T is equal to the energy. Okay. Now, why can I use QMC, excuse me, why can't I use QMC delta T, Q equals MC delta T, for parts 1 and part 4? Well, I already told you that, and your answer should be because that's a flat line. There is no increase in temperature. Okay? Because delta T is 0, temperature is not changing. So, how do we calculate the amount of energy required during a phase change? Because if you look right back here, this is the part right here where we are changing. It's the melting point. So we're changing from a solid to a liquid. This up here, the phase change, it is the boiling point. We're changing from a liquid to a gas. So how do we calculate the amount of energy needed for that phase change? We can use either the heat of fusion, which we have HF, or we can use the heat of vaporization. So in order to determine the energy of the melting, when we have melting going on, that's the heat of fusion, we take Q is equal to the mass times the heat of fusion. When we have vaporization going on, when we have the boiling point, we have the heat of vaporization, okay? Q is equal to the mass times the heat of vaporization. So Q equals mH sub F, Q equals mH sub V. We use these two constants instead of a specific heat in the delta T. Let me move these out of the way so you can see that a little bit better, okay? Heat of fusion is the amount of energy required to change 1 gram of a pure substance from a solid to a liquid at its melting point. Once again, we talked about this. You are not changing the temperature. That's where we have that plateau in Roman numeral number 2. Okay, so we're not changing the temperature. The heat of fusion is a physical constant. Okay, it is a physical constant. So I'm going to go back here to this data table. All right, I'm going to have to get what you wrote on. Keep what you wrote here down, but I'm going to have to get this off of my chart here because it does not move with the chart. So we're going to go back here to the top part of this chart. You can see right here on the chart, here is the heat of fusion. All right, the heat of fusion. And notice the label right here. That label is kilojoules per kilogram. What you're going to see when we are doing this, we're not going to want to use kilojoules per kilogram. So we will be using joules per gram. And those values are going to be the same as these values that we have listed in that column here. Because what we would do in order to convert that from kilojoules per kilogram is we would take 1,000 over 1,000, which is actually 1. Okay, so I can just say, instead of kilojoules per kilogram, I can just say joules per gram. So if we're looking at this particular table and we're saying, okay, what is the heat of fusion for water? The value that we're going to need here is going to be that 333 joules per gram. I'm going to switch now back onto the PowerPoint. Okay, so here we go back with the heat of fusion. So the H sub F there would be 333 joules per gram based on our reference table. How much heat is absorbed when 10 grams of ice melt at 0 degrees Celsius? Remember, I just said heat absorbed, that's going to be Q. Mass of the substance is going to be M. Heat of fusion is going to be H sub F. So when we have our specific equation, it's going to look like Q equals M H sub F. I'm going to go ahead and make this change here because these notes don't agree with the data table. So I'm just going to change that slightly here. So what I'm going to see is that this is also going to change my answer to be that. So let me get that back. Now we've got that value matching our chart. So 10 grams, which is going to be right up here, 10 grams of ice, 10 grams. The heat of fusion is 333 joules per gram. So what we're going to see is that we're going to need 3,330 joules of energy in order to melt 10 grams of ice. Where does this energy go? Well, the particles must overcome forces of attraction to move further apart during a phase change. If you can remember, solids are packed very, very tightly together. Okay? Liquids are not quite packed so tightly together. Those were the notes that we did the other day. So we know that a solid is packed more closely together than a liquid. That's due to the attractive forces. So the particles must overcome those attractive forces in order to go from the solid state to the liquid state. Heat of vaporization. Okay? The heat of vaporization, as I can see here, folks, heat of vaporization is the amount of energy required to convert 1 gram of a pure substance from a liquid to a gas. So we're going from a liquid to a gas at its boiling point. Once again, you are not changing the temperature. This is that plateau. This is Roman numeral number 4 on our chart there. The plateau, the change in temperature is nothing. For water, that's going to be at 100 degrees Celsius because that's the BP, the boiling point of water. It is also a physical constant. Okay? So as I'm looking here, I am going to go back to the reference table. Here we go. Here's our handy dandy table. Now once again, here is our heat of vaporization. We have the same problem. Okay, we have the same problem with our labels, but like we just talked about, that's going to be joules per gram. So make sure you make a note out of that. Okay, make a note of that. And when we come down here to water, there is our value. So the heat of vaporization of water is 2,260. Okay, so that is the heat of vaporization. Let me swing back. Okay, so now our equation is going to be Q equals mHV. So this equation right here, the Q equals mHV, goes for Roman numeral 4 on our table. How much energy does it take to vaporize 10 grams of water? Once again, Q, energy, equals M, the mass, times the heat of vaporization. Mass is 10 grams. We just got the heat of vaporization from our chart, which is 2,260 joules per gram. When I multiply those together, I get 22,600 joules. Okay? That's a substantial amount of energy compared to what we had before for the heat of fusion. Okay? The amount of energy to go from a solid to liquid was, I believe, 3,330. Well, this is 22,000, so it's somewhat larger. It takes more energy to go from a liquid to a gas than a solid to a liquid. Why? Here we go again. There's that value. I'm going to change that. Okay? Why? Okay? Why? Water is changing from a liquid to a gas. It requires 22,600 joules per gram. Water changing from a solid to a liquid requires 3,330 joules. Why? Okay? Greater energy is required to change from liquid to gas because the particles are spreading even farther apart. Okay? Even farther apart. So now, what I would like you to do is you need to write this, draw this very diagram into your notes. And I'm going to pause the recording to let you do that, and then we're going to talk about this again. Okay, now we're back. We've got the 5 different areas of our chart, and I labeled them Roman numeral 1, Roman numeral 2, Roman numeral 3, Roman numeral 4, and Roman numeral 5. Now, if you remember before, we could do the Q equals MC solid delta T, okay? So we have this. If this were water, this would be ice. Now we have the boiling, or excuse me, check. We have the melting point. There's no change in temperature, so we have to use Q equals mH sub F, the heat of fusion. Now we have a liquid. We're increasing the temperature. So we're going to take the specific heat, C of the liquid, the mass, and the temperature. So Q is equal to the mass of the liquid, the specific heat of the liquid, and the change in the temperature. We flat-lined here, okay? We flat-lined here, so we have the boiling point. Once again, there's no change in temperature, so we can't use the delta T. We have to use the equation Q equals mHV. So the mass of the substance and the heat of vaporization. So this is 4, and it was where we have the boiling occurring. And finally, part 5 of the graph, Q is equal to the mass, the specific heat of the gas, times the change in temperature. You can see we are increasing temperature again. So this whole chart is very important when we continue talking about these calculating the energy changes at phase changes. Here's the first example problem that we are going to do. How much energy does it take to raise the temperature of 12 grams of water from minus 25 degrees Celsius to 125 degrees Celsius? I'm going to give you a little time here. Pause the video so that you can write down that equation. All right, we're back here, folks, and we've got the equation with the problem written down. So we need to do this in 5 different steps because you have the 5 different areas on the chart. So remember the 5 areas here? We're going to have step 1, step 2, step 3, step 4, step 5, and you're going to notice that we're going to use these values for Q for each 5 of the steps. So let's go back to step 1. Here we go on step 1. We know that in step 1 that Q is equal to m C of the solid delta T. What was our mass for this one? Well, go back, the mass was 12 grams, 12.0 grams of water. So my mass is 12 grams. My C of the solid, I need to go to my reference table. And when I went to my reference table, I'm not going to click up to it, but you should have that reference table out at your desk. If you look on the reference table, the C, the specific heat of ice, is 2.100 joules over grams times degrees Celsius. And what is the delta T? Okay, what's very important about this is that you know the melting point of water. Okay, because we started at we started at minus 25 degrees Celsius. Okay, so water will start to ice will start to melt at 0 degrees Celsius because I know that's the melting point of water. So my delta T is going to be my final temperature, for this case 0 degrees Celsius, minus my initial temperature. In this case, that's going to be minus 25. So I'm going to have 0 minus a negative 25. Once again, 0 minus negative 25. So that's going to give me a value of 25. Okay. Now, the question was asked before. Okay. Here's what I'm going to have, my calculation. The question was asked before, since we have a temperature here, why are we not converting this to Kelvin? Well, the simple reason is that even if we would add 273.15 to all of these values, the change in the temperature is going to be the same. Okay, so the change in temperature is going to be the same whether I am in the Celsius scale or I'm in the Kelvin. Okay, reading temperature in Kelvin. So when I put this all together and do my multiplication, I come up with phase 1, okay, with chart 1, Roman numeral 1 is going to be 630 joules. I move on to Roman numeral 2. If you remember, Roman numeral 2 was the flat line dealing with the melting point. We don't have any temperature change, so we have to use the equation Q is equal to mH sub F. In this case, once again, our mass is the same. It's 12.0 grams of water. The heat of fusion for water was 333 joules per gram. Therefore, when I do the math and put it all together, I get 3,996 joules. Where did I get 333 joules per gram? That is the heat of fusion of water, and I got that off of my reference table. Let's move on then to Roman numeral 3. Okay, we have a liquid now, so we are on the liquid, heating up our liquid. So I'm using the equation Q is equal to M, the specific heat of the liquid, times the delta T. Once again, mass is 12 grams. The C of the liquid, I go back to my reference table. C of the liquid is 4.186 joules per gram times degrees Celsius. And finally, my delta T. Now for this one, remember, my delta T, I'm going to take this from where I just started heating after it was a liquid. I'm heating my liquid up. What's my boiling point going to be for water? It's going to be 100 degrees Celsius. So my initial temperature is going to be 0 degrees. My final temperature is going to be 100 degrees, because that's the melting and the boiling point for water. So my delta T will end up being 100 minus 0, which is 100. So here are my values that we were just talking about. When I multiply those together, I'm going to get 5,023.2 joules. Moving on now, section 4 of my graph. Section 4 is the boiling point. When I look at the boiling point, once again, I am not increasing the temperature. So I do not have a change in temperature. So I need to use the equation Q is equal to M, the mass, times the heat of vaporization. Once again, my mass was 12.0 grams. My heat of vaporization I'm going to get from my reference table for water. It's 2,260. So Q is equal to M H sub V. M was 12 grams. 2,260 joules per gram is the heat of vaporization based on my reference table. When I multiply those two together, I get 27,120 joules. So that's my energy for step 4. And then finally, we're going to go on to step 5. We have an increase of temperature, okay, in step 5 once again. So I can use Q equals the mass, the specific heat of the gas, and the change in the temperature. Now, mass once again is 12 grams, 12.0 grams. The specific heat of the gas from my reference table once again is 2.010 joules over grams times Kelvin. And my delta T. Well, let's remember, where am I starting off at? Now I'm starting off at the boiling point. So that boiling point is 100 degrees Celsius. Where did I go to? Well, my final temperature was 125 degrees Celsius. So I'm going to take my final temperature, 125, minus my initial 100. So 125 degrees Celsius minus 100 degrees Celsius is going to give me 25 degrees Celsius. So when I look at my values, 12.0 grams, 2.010, and 25, I multiply those together and I get 603 joules. Now, I'm not done yet because I want the total change in energy. So for this particular one, I am going to take all 5 of the energies that I just calculated and add them together. So as I take all 5 of these and add up these 5 values, I get 37,372.3 3 joules. Now, what WebAssign is going to ask you to do is WebAssign will ask you to convert that into kilojoules. So what I'm going to do is I'm going to take my decimal point, and to go from joules to kilojoules, I'm going to jump at 1, 2, 3 spots to the left, so that gives me 37.3723 kilojoules. I go back to my original problem, and I see that I have 2 significant figures because my temperature was 25. That was the lowest amount of sig figs. So I'm going to put this to 2 sig figs. So my amount of energy that I'm going to write down when WebAssign is going to ask me is going to be 37 kilojoules for my total energy. This has been day 1 of the calculating energy changes at phase changes. I'll see you later for day 2 notes.